Good morning to everyone. Myself, I am G. Charan from Tripoli branch. Today's my topic of MTT is application of the Laplace transform in the solution of linear integral equations. In mathematics, the Laplace transform named after its inventor Pierre-Simon Laplace is an integral transform that converts a function of a real variable in the time domain usually to a function of a complex variable display style in the complex frequency domain also known as S domain or S plane. Yeah. Complex frequency domain also known as S domain or S plane. The transform has many applications in science and engineering because it is a tool for solving equation differential equation. In particular, it transforms ordinary differential equations into algebraic equations and convolution into multiplication for suitable function. The Laplace transform is the integral of display style. The theory of integral equation is very useful tool to deal with the problems in applied mathematics and engineering applications. Here, the theory of integral equation is very useful tool to deal with the problems in applied mathematics and engineering applications. A large class of initial and boundary value problems can be converted to Volterra or Fredholm integral equation. Here I discussing the basic concept of integral equation and the solution of Volterra integral equation by using Laplace transform. Constructing examples are also provided to illustrate the ideas. The result reveals that the transform method is very effective and convenient. Yeah. Constructive examples are also provided to illustrate the ideas. The results reveals that the transform method is very effective and convenient. Here we can see keywords like integral equations, Volterra integral equation, Fredholm integral equation, Laplace transform method, linear and nonlinear integral. Many of the physical problems of engineering science, which were solved with the help of ordinary and partial differential equations. This can be done by better methods of integral equations. The Laplace transform is an integral transform named after its inventor Pierre-Simon Laplace. It transforms a function of a real variable of time to a functions of a complex variables complex frequency. The Laplace transform is an integral transform named after its inventor Pierre-Simon Laplace. It transforms a function of a real variability of time to a function of a complex variable. The transform has many applications in science and engineering. The current widespread use of the transform is mainly in engineering. Came about during and soon after World War II, replacing the earlier heaviside operational calculus. The advantages of Laplace transform has been emphasized by Gustav Dostek, to whom the name Laplace transform is apparently due. Integral equation. An integral equation is an equation in which an unknown function appears under one or more integral signs. For example, for a less than x less than b, a less than t, t less than b. The equations y of x is f of x plus lambda integral a b k of x comma t y of t dt, where the functions y of x is the unknown functions while the functions f of x and k of x comma t are known as functions, and k of x comma t is called the kernel of the integral equation, and lambda a and b are constants. Linear and nonlinear integral equations. An integral equation is called linear if only linear operations are performed in it upon the unknown function. An integral equation which is not linear is known as a non-linear integral equation. L of y is equals to y of x minus lambda integral abk of x comma t y of t dt. We can easily verify that L is a linear integral operator, in fact, for any constant c1 and c2. We have L of c1 y1 of x plus c2 y2 of x is equals to c1 L of y1 of x plus c2 L of y2 of x, which will well known general critical for a linear operator. Classification of integral equation. Fredholm integral equation, a linear integral equation of the form g of x y of x is equals to f of x plus lambda integral bk of x comma t y of t a dt of 1, where a b are both constants. F of x, g of x and k of x comma t are known functions, while y of x is unknown functions and lambda is a non-zero real or complex parameter is called Fredholm integral equation of third kind. The functions k of x comma t is known as the kernel of the integral equation. Fredholm integral equation of the first kind, a linear integral equation of the form putting g of x is equals to 0. F of x plus lambda integral a b k of x comma t y of t dt is equals to 0 is known as Fredholm integral equation of the first kind. Fredholm integral equation of the second, linear integral of the form by setting g of x is equals to 1 in 1. A linear integral of the form by setting g of x is equals to 1 in 1. Y of x is equals to f of x plus lambda integral k of x comma t y of t a b dt of 3 is known as the Fredholm integral equation of the second kind. Homogeneous Fredholm integral equation of the second kind, a linear integral of the form by setting f of x is equals to 0. Y of x is equals to lambda integral k of x comma t y of t b a dt is known as the homogeneous Fredholm integral equation of the second kind. Volter integral equation, a linear integral equation of the form g of x y of x is equals to f of x plus lambda of f of x plus lambda of integral x k of x comma t y of t, where a b are both constant. F of g, g of x and k of x comma t are known functions, while y of x is unknown functions and lambda is a non-zero real or complex parameter, is called the Volter integral equation of third kind. The function k of x comma t is known as the kernel of the integral equation. Integral equations are defined and references are given to the Laplace transform technique. Most of the operations used are illustrated through a solution of Abel's integral equation, it is shown that the Liouville-Newman series follows logically from an operational solution of Volta's integral of the second kind. Whittaker obtained solutions to the integral equation with the general expressed in the last three forms. His procedure was quite involved and it showed her that the same solutions are obtained more directly through the operation calculus based on the Laplace transform. The integral enumerated here are those termed defined integrals, which can be interpreted as the signed area of the region in the plane that is bounded by the graph of a given functions between 2 points in the real line. Conventional areas above the horizontal axis of the plane are positive while areas below are negative. Integrals also refers to the concept of an antiderivative of a function whose derivative is the given function in this case. They are called indefined integrals. The fundamental theorem of calculus related defined integrals with the differentiation and provides a method to compute the definite integral of a function when its antiderivative is known. All through methods of calculating areas and volume dated from ancient Greek mathematics, the principle of integration were formulated independent by Isaac Newton and Gottfried Wilhelm Leibniz in the late 17th century, who thought the area of curves infinite sum of rectangles of infinitesimal width. In mathematics, the Laplace transform, named after its inventor Pierre-Simon Laplace, of an integral transform that converts a function of real variable in the time domain, to a function of a complex variable displaced in the complex frequency domain, are also known as a domain or S-plane. The transform has many applications in science and engineering because it is a tool for solving differential equations. In particular, it transforms ordinary differential equation into algebraic equation and convolution into multiplication for suitable functions in the Laplace of transform integral. Thank you.